Let's move on a little more into sort of the meat of what we wanted to cover in this lecture. And let's start with the elastic to plastic deformation. And as we really look at this transition, we had talked in the previous lecture about this linear portion. We concentrated on that where we had Hooke's law, and we had this area where if we applied a load to a material and it strained within this area, that it would return to its original shape. We're going to move away from that a little bit and really start to think of what happens when we keep applying load and we start permanently deforming it. For most metals, we know that the elastic deformation only goes to about 0.005 as a number for strain. And we can look at that as percentages, about 0.5%. So it's not a really large strain. And in most of our applications, that's great. But if we keep going past it and we go beyond this letter P, and this is an important thing to note, if I were you, I would write this down, is that P represents the proportional limit. It's not the yield strength. What it is basically that gradual change from a linear to a nonlinear behavior on the stress strain curve. It's very difficult to pinpoint. If I were to ask several of you what the proportional limit here was, I would get a range of different answers around there. And as we had talked about certainty and being able to produce the same number time and again is important in mechanical testing. Proportional limit doesn't really give us the ability to do that. It is that transition. It's an important point to know. But what we need to do is really find out some way of determining what we consider the yield strength. Because when we think of yield strength, that's where we really think of this transition from elastic to plastic behavior. And what we see here is the convention to do that is to accept a certain level of strain, this 0.002. And what we tend to see here is if we draw a line parallel to the elastic deformation portion of the curve with this 0.02 or 0.002 offset, we're going to see it used in literature as 0.2% offset yield strength. And if we draw a parallel line, what we come up with is another number up here, but it's a number that we can consistently obtain, much more consistently than we can the proportional limit. So whenever we talk about yield strength in the class, it will be spoken of as this 0.2% offset yield strength. And we see it schematically shown here in the diagram. So let's think about how we determine mechanical properties from the stress strain curve. We've talked about how we're going to obtain these. And as we start to look, we see in this inset of how the yield strength is determined. So going back again, our modulus of elasticity. What's the modulus of elasticity? And we're going to use this stress strain behavior for this brass specimen here. Our modulus of elasticity is that E value that we remember from Hooke's law. And what the E value, or this capital E is basically the slope of this line. So what we can do is use our knowledge of what we learned back in algebra years ago of the change in the Y over the change in the X-axis values. And we can see that in this brass specimen, it comes up to about 93.8 or 94 gigapascals. And modulus of elasticity, we noted this when we talked about Hooke's law, is always in units of gigapascals. It typically is for the metals. And so it's a good check on whether your calculations are right, whether you come up with that level of those units, those types of units for the modulus of elasticity. Now, what's the maximum load? We know that we can measure load from our engineering stress strain curve, our definition of engineering stress. So let's assume that we have a 12.8 millimeter diameter bar, and we know that the force equals the stress times that original area because we're using an engineering stress strain curve. We can take what our cross-sectional area will be for that bar that we're going to look at and be able to determine, based off what that is, of really that maximum load. And in this case, we know that the maximum load that this bar can withstand is going to be what we consider the tensile strength, which corresponds to this maximum value on the stress strain curve, and we see it defined here. And that's where we come up with our stress for that maximum load. And then the change in length. If we know what the original length is and we know a certain stress level, in this case we're going to take about 345 megapascal for that stress level, the first thing we need to look at is that it is plastically deforming. And we're just going to look at the instantaneous change, or that delta L. We're not going to worry about the spring back or the elastic component to what the strain would be, but we see that it'll strain 15 millimeters, which, for a 250 millimeter long bar is a pretty significant amount, and it's something that we would noticeably change. So just using a stress strain curve, a couple of ideas of this case, a brass specimen, it would be different for different materials. We can determine a pretty good amount off of what it is, off of what's happening with this material, with a pretty minimal amount of other information, just what we can take from the curve itself. So the question becomes, let's take a little closer look at this, but how do we define tensile strength, or this maximum strength that the material will be able to withstand? And we saw from the previous one that typically the units of stress are going to be in megapascal if we use the MKS units. As you work in industry a little more and you start working with older engineers, what you'll see is a lot of them use PSI, or what they call KSI, which is just 1,000 pounds per square inch. PSI is pounds per square inch. And with this, we see that the stress at the maximum level defines that tensile strength, or what we call the ultimate tensile strength. So we have our linear elastic region. As we go past our proportional limit, which is the point where we leave linearity, we start to strain harden the material. We're going to get into that a little bit. We see the strengths increasing, continuing to increase, even though we're producing enough strain to plastically deform the material. And so what we would see in a material is that it would uniformly change length, and the width would decrease in a similar way. And as we reach our maximum, we reach our ultimate tensile strength. But as we go past that, we see the stress start to decrease. And what's happening here is that we start producing a phenomenon called necking, where we have a localized thinning. If we remember our initial videos that we saw, change in length of the piece of rebar, we saw the necking occur prior to failure. And then what we will see is the ultimate fracture or failure of the part, where it will break in two. And so these are the components we have, but this is a materials class. And so we're going to be primarily interested, since it is a materials class, to be able to see how different materials produce different stress strain curves. And in this case, we see what the difference between a ductile material, which is simply one that's going to show a large amount of plastic deformation prior to fracture, and a brittle material, where we have little to no plastic deformation. And thinking of some materials that may have some of these differences, brittle materials typically are the equivalent of what we would look at as ceramics, or one. Certain metals, we see a less than 5% strain. There are certain metals that will have less than 5% strain. Some grades of titanium fall within that area. Some grades of magnesium have rather low if they're not properly heat treated. And so we can produce metals that are brittle. And if we heat treat a steel improperly, it will also display brittle behavior. And so we have this idea of the ductility. The other thing that we can look at when we start looking at the difference between ductile and brittle materials is this idea of toughness. Sort of hit upon it in the important terminology section early on, but really toughness is just the area under the stress strain curve up to failure. And so we can see in the schematic figure here that we've borrowed from Callister that the toughness of this ductile material far exceeds that of the brittle material if we look at the area under the curve up to failure. And from a physical standpoint, rather than just looking at it and saying, yeah, toughness is the area under the curve, what we look at as toughness is the ability of the material to absorb energy prior to fracture. And we define toughness generally like this, but what we're going to see as we start moving forward and we start getting into a little bit of what we consider to be fracture mechanics is really the study of crack growth or crack initiation and propagation in materials. We're going to see that we measure toughness, and toughness becomes a very important consideration when we start really looking at how materials fail. So I would recommend that you really keep an understanding, keep it in the back of your mind that toughness is this ability of a material to absorb energy up to fracture. And toughness really becomes the ability of that material to hinder crack propagation. The cracks may initiate, but if the material has high toughness, it doesn't allow the cracks to grow. So the cracks grow at a much slower rate. If you have a low toughness material, cracks will rapidly propagate and you will have failure much more quickly. So let's look at a couple of failure of ductile materials. In this case, you see that we have a couple examples which are basically brass and annealed copper. So let's look at the naval brass first and lower the volume on this. And so we're just going to really look at how this material fails. If you see it pretty quickly, it's not a real well controlled test because you can see necking occurring pretty quickly, not in the middle of the test specimen. So as we start talking about tensile testing, what we're going to see is this area where we really want to start having the failure occur. We're going to call that the gauge. And in this case, that's a rather long gauge, and there's not a lot of control. And so as we see how the material continues to fail time and again, and in this case, what we see is the remnants of a ductile failure. Now, this was another test that we would have where it's annealed copper. And in this video, what we would see is this test, this annealed copper, because the copper is annealed, it's going to show much greater ductility. And we'll get into what annealing is. Annealing is a heat treatment that allows us to really soften materials. And it's going to become an important consideration when we start thinking of how materials are processed and how you receive them as a structural engineer. Say you're going to fabricate a large structure, and you want to be able to bend and take a shape of annealed copper into something that you want. And I always go back, you will see this pretty good idea of this if you do pipe bending for plumbing type applications. Now, what happens to brittle materials? And so concrete is a great example of a brittle material. And what we're going to see here is concrete's typically designed to be placed in compression. If we look at most of our structures, we'll see that. And in this case, we'll get an idea of what happens when you start compressing concrete. Rather dramatic. And since it's not a very long video, we'll show it again. And what we see is, unlike the brass where you saw necking, you saw a lot of plastic deformation, do you really see anything happen before the concrete, for the most part, explodes? Even in compression, you really don't. Let's look at what happens when we put the concrete in tension. And so what we're going to really see here is we saw some parts blow out there, some of the other components, because concrete is just a collection, for the most part, of cement and sand and some rock. But do you see any movement, any change in strain? They're literally trying to pull that. You don't see necking. You see really no idea that that is getting longer or shorter or anything. And we see how it fails. It just really comes apart. And so without that change in strain, what we have is the idea of a brittle material. So going from a brass or a copper to a concrete are two real extremes of what ductile and brittle materials. So how do we define ductility? So ductility, going back, is that change, that strain that we saw, and some way of being able to define that. And there's two ways that we look at it: percent elongation and percent reduction in area. So what we're doing is we're taking that strain that we're measuring and we're giving it a percentage value. And it can either be that strain in the linear orientation or the percent reduction in area. In a lot of cases, what we're going to be looking at, especially as we start doing tensile testing, is a cylindrical type sample with a gauge length. And within that gauge length, we're able to measure that change in diameter. And that's all the percent reduction in area is. Imagine just a circle, and as it changes, we go back to what we thought of with Poisson's ratio. And so we can have percent elongation, so we take our final length, subtract our original length from that, and divide it by that, so we get a strain, and we just take a percentage of it. Same with the reduction in area. It's just that original minus the final cross-sectional area of what we're looking at. So that can be a cylindrical, it can be a square, it can be any type of shape. We're able to measure that area. So what about these common materials and some of their mechanical properties? And we start looking at it. Common materials and alloys are all over the place. Let's look at the yield strength of pure iron versus even that of molybdenum or even to aluminum. And this sort of comes down to why we really start looking at these. What we see is the brass. We go from copper to a brass, and the big difference is that change in elongation. And so we start to see why we use alloys for different applications, just taking something from a copper, and in this case with a brass, adding about 30% zinc. We get a kick in elongation, we get an increase in tensile strength, and we get something that's a little bit stronger in the yield strength. But this allows us with brass to be able to change its shape. Imagine hot water piping and being able to do tube bending and pipe bending with that. Another one is we see with steel, we add 0.2 weight percent carbon to a steel, and we look at what happens with the iron. And we'll get into this when we start talking about alloys a little more. But what we see here is really that change. We see a decrease in elongation, but you really are buying the tensile strength increase and the increase in yield strength. And we see that titanium and molybdenum are far above any of these. But in a lot of cases for these types of yields and tensils and elongations, you're going to be paying for it. So what about temperature effects? Now, we go into popular culture a little bit. The Terminator movies were a great example of this, particularly in cases where there just happened in a Terminator movie to be some liquid nitrogen sitting around, and the Terminator didn't fare very well. And what we see with that is we decrease temperature. So 25 degrees C, just as a reminder, is where we have for room temperature. Negative 100 C, we get something that has a higher yield strength, and our proportional limit has definitely increased. But look what happens to our strain, our elongation. What we start to see is our ductility starts going down. And if we go to minus 200 degrees C, we see this significant decrease. We see almost no elongation. What we've done is we've transitioned from a ductile material to a brittle material. And we'll get into how we measure a transition from ductile to brittle previously. Another component from popular culture is the Titanic sunk because of this change in temperature and this transition from a ductile behavior of the steel to a brittle behavior of the steel. We'll talk a little further about that in some lessons to come. But the one to think is we see that yield and tensile strengths can decline with increasing temperature, but the ductility will increase, especially at these temperatures we're talking about. But the modulus elasticity, or that sort of measure of the stiffness, doesn't change very much. We see that the elastic portions of the curve sort of fall upon each other. So it's within this plastic deformation region that we start to see these effects of temperature.